Alright, so this time we're looking at for the mechanism for the chlorination of benzene. So yet again, we're looking at another halogen involved in this mechanism where chlorine is added to benzene. And the first step in this then is, again, it's electron movement again, and it's a catalyst FeCl3 that must be present in this case. So it isn't the UV light this time; it's a catalyst that actually causes the electrons in the bond electrons, if you like, in the chlorine molecule, causes the electron to pass from, or to be grabbed by one electron and to be lost by another. Okay, so when we have this transition then of the electron by the action of the catalyst, we end up with the Cl minus, as I said, and the Cl plus as indicated here. So we have the Cl plus. Now you notice that the Cl minus actually bonds with the catalyst. It was FeCl3, it's become FeCl4, and it's also got a negative tagged onto it, okay, and that's coming from this Cl minus here. So we've made something that was neutral now have a negative charge. Okay, so now we have a electrophilic portion. The electrophilic would be the Cl plus here. This wants electrons, it likes electrons would be the idea there. It's a Cl plus. It needs a negative then to be made neutral, or it can bond with the negative. That would be the point. So then we have to look at exactly how that can happen and where can this electron come from. Okay, so if you look at the benzene ring that we have here, then okay, we've got some double bonds in it. Okay, so then that means that we have a region of quite a lot of negative charge. We've got an electron rich area. Okay, and in these cases then, if these two go and bump adjacent to one another, if these two pass close to one another and collide, then there's every chance that this bond will break basically, and we will have a dangling bond then that needs to attach to something. Okay, look, it's just as well to at this point to include, you know, what are the elements that are in benzene. And okay, so look, this is C6 H6. That's what we're starting off with. We've got our double bonds here as indicated, a resonance structure. We have our hydrogens on the outside, but if you check, you'll see that there's 4 bonds between every carbon, and that has to be the case. So from carbon to carbon you have a double bond, and then you have 2 single right there, and for this one here then you have a double bond again, a double bond that resonates, if you like. Okay, so this double bond that's here will in the next minute appear here, moments, microseconds we'll say, will be here, and that's the resonance in the structure. Okay, but in any case, what I've done is I've indicated in a double bond, I've indicated one of the bonds in the double bond, and I've indicated the electrons at each end of it. Okay, so we've got the blue colored electrons, and this is the case that we talked about in a collision between the Cl plus and this double bond right here. What's going to happen is that double bond is going to dangle out there like that, and you can see I've indicated the color of the electrons again, blue for blue, and this electron then is going to bond with the chlorine, which was Cl plus. It was electrophilic, it needed electrons, and now it has sourced an electron, and so it's quite content at that point. Okay, and that's all good, except for the one thing, that we have a positive charge here now. This carbo, there is a carbon here, remember? So we've got a carbocation, we've got a positive charge right there, and that just needs to be stabilized for the atom to be neutral entirely. So I mean, what are the options? Yeah, we do have a negative here, okay, and it is possible that there could be a bond between the negative and the positive, But if you look at the proximity of these, we've got that dangling H there. It's much more likely that this one is going to be snapped up, if you like, by, well, it's called a base. Okay, and a base is a proton acceptor, and therefore if it's a base and this is a proton, then the base is going to accept the proton. So there's another good reason why you've got proximity in the fact that this behaves like a base. So therefore the H is going to be snatched by this base. It is negative, so it's looking for a positive. Therefore the electron is going to be left behind. It's going to take a proton, so the electron that the hydrogen has in this bond, the orange, I've got two of them in that bond. It's a carbon to hydrogen bond, but this electron is going to be left behind. This is going to be H plus then, which is going to bond with the Cl minus that's in the FeCl4 minus. And therefore you're going to be left with an orange electron right here. And guess what? The door is going to close there with the extra electron right there. That negative is going to be attracted directly to the positive, and there you see the final result down there. You see the orange electron right here, and this one centered just up here as well. And then we have our stable molecule. We have Cl attached, bonded. We now have this H here, which was that H right there, bonded with the Cl minus. That was the Cl minus that made this negative in the first place, and we're left with our catalyst. As by definition, catalysts are unchanged in the final analysis, and you can see that that's the case here. And just for your clarity as well, what I've done is I have shown the 4 bonds that we have. So I've just color coded them. So centered on this carbon right here, we have a brown, orange, light blue, sky blue, and dark blue. And you see the way they bond then with their corresponding electrons. And that pattern follows through. We have the orange electrons of the hydrogen. You can see them right there as well, and you can also see the final location for these electrons just at the end of the reaction. We've got a double bond re-established here again. We still got our brown electron pair there, the bond pair, the blue electron bond pair that we got from this original breaking bond up here. So study the changes and it should make some sense to you. And that's that. And just for your information, it says that a neutral substitution product forms. Now remember, we don't normally associate substitution with double bonds, like we have double bonds right here in this resonance structure. We usually associate substitution with saturated bonds, meaning that there are no double bonds, and so therefore we would expect addition to be the case in this, but it ends up that we no longer have a hydrogen here, we now have a chlorine, even though at the intermediate stage we had both. Okay, but at the final stage, in the final analysis, it is just a substitution in the end, and we are left with our double bond intact again.